first part of the spectral theorem says that every Hermitian matrix is guaranteed to have real eigenvalues. What does the second part say? The second part of the spectral theorem says that the eigenspaces of a Hermitian matrix S are guaranteed to be orthogonal to one another. So in the motivational example we gave, we saw an example where we had an ordinary 2x2 and a Hermitian matrix, and we looked at their eigenspaces side by side, and we saw that the ordinary matrix had eigenspaces that were not orthogonal to one another, and we saw that the Hermitian matrix had eigenspaces that were orthogonal to one another. The second part of the spectral theorem says that this is guaranteed to happen. I want to show the proof of this part of the spectral theorem, and this is a little bit more complicated than the first part, but again, I still think it's useful to see the steps one by one. So let's walk through the steps here. We're going to choose an eigenvector v1 corresponding to an eigenvalue lambda 1, and then we're going to choose another eigenvector v2 corresponding to another eigenvalue lambda 2. So here, lambda 1 is assumed to not equal lambda 2, so that we know we're working with different eigenspaces. And the two eigenvectors we're choosing here are called v1 and v2. Our goal is to show that these two vectors are orthogonal to one another, which means we want to look at their inner product and argue that this inner product equals 0. It's going to take us more steps to get to the conclusion than it did in the first part of the spectral theorem, but I think the steps are kind of interesting. So let's look at the inner product of v1 with v2. Well, again, our strategy here will be to multiply this quantity by the number 1, but we're going to choose the number 1 in a clever way. We're going to take the difference between lambda 1 and lambda 2 and divide by that same number. Here we know that the difference, lambda 1 minus lambda 2, will not equal 0 because we are assuming that lambda 1 does not equal lambda 2. Well, what can we do after we multiply by 1 here? One thing we can do is we can take the numerator of this scalar and push it into the second entry in our inner product. So now our scalar on the outside of the inner product is 1 divided by lambda 1 minus lambda 2. And we're looking now at the inner product of v1 with the quantity lambda 1 minus lambda 2 times v2. Well, now we can look at this second entry in our inner product and distribute the v2, so which gives us lambda 1 times v2 minus lambda 2 times v2. And we can take the inner product now and we can distribute it. One of the properties of inner products is that they're conjugate linear, which means that we can distribute inner products in either slot. Here, a lambda 1 factors out, and then in the second position, we know that lambda 2 times v2 is guaranteed to equal s times v2 because v2 came from the eigenspace of s where the eigenvalue was lambda 2. So after distributing, we're left with lambda 1 times the inner product of v1 with v2 minus the inner product of v1 with s times v2. One thing we know about the eigenvalues of any real or of any Hermitian matrix is that the eigenvalues are guaranteed to be real. So this lambda 1 in the curly braces here is actually equal to its own conjugate transpose. So by conjugate it's equal to its own conjugate, and by conjugating we are not changing the expression then. And the reason for conjugating lambda 1 here is because, if we conjugate lambda 1, we know we can push it into the inner product in the first position. So now we know that this conjugate lambda 1 times v1 is actually the same as lambda 1 times v1. And we can then use this expression to write lambda 1 times v1 equals s times v1, because lambda 1 was an eigenvalue for our matrix S, and v1 came from that eigenspace. So we know lambda 1 times v1 is the same as S times v1. Well, now we know that, we have S on the left side of this particular inner product, And we can always move matrices back and forth inside of inner products, but we have to conjugate transpose whenever we move. So we can move this S on the left-hand side to the right-hand side by conjugate transposing. But we are also told that S is Hermitian, so S star is actually equal to itself. And now we see that this a quantity in the curly braces is actually equal to 0, because we're looking at V1 inner product with S times V2 minus V1 inner product with S times V2. So this entire expression is equal to 0. So once again, we started with an expression, which in this case was V1 inner product with V2, and we wrote down a bunch of equalities, and we ended with the number 0. So this is our successful argument that if we choose two eigenvectors coming from different eigenspaces, their inner product is guaranteed to equal 0, which ultimately means that our two eigenspaces are orthogonal to one another. So this concludes the second part of the spectral theorem. The eigenspaces of any Hermitian matrix are orthogonal to one another. So let's see an example that illustrates this point. Here we have the data of a 3x3 real symmetric matrix. And remember that real symmetric matrices are always Hermitian. So we shouldn't be surprised to find that this real symmetric matrix has real eigenvalues. And those real eigenvalues are 6 and 3. What we found here is that each of these eigenspaces has bases that someone has provided for us. For lambda equals 6, the eigenspace is one-dimensional, and our basis vector is 1, -1, -1. And for lambda equals 3, our eigenspace is two-dimensional, and our basis is 1, 0, 1, and 0, 1, -1. So what the second part of the spectral theorem says is that these two eigenspaces should be orthogonal to one another. We can verify this ourselves by taking a dot product of the one basis vector for the eigenspace where lambda equals 6 with both of the basis vectors for the eigenspace where lambda equals 3. So our first dot product here should be between 1, -1, -1 and 1, 0, 1. Well, this dot product is 1 plus 0 minus 1, which is certainly equal to 0. And our second dot product should be between 1, -1, -1 with 0, 1, -1. Here, of course, the dot product is 0 minus 1 plus 1, which also equals 0. So here what we have is a verification that the second part of the spectral theorem is actually working for this particular example. So in particular, these calculations verify that the eigenspace of this matrix S for lambda equals 6 is indeed orthogonal to the eigenspace of S where lambda equals 3. And of course, this was expected, so this calculation was unnecessary because we know that S is real symmetric and therefore Hermitian, which means that part 2 of the spectral theorem applies to this matrix. So before we even did these dot products, we knew that these two eigenspaces would be orthogonal to one another because this is an example of a Hermitian matrix.